Hello everyone. Today we are standing on week 3 of the Physics Basics course, and today on session 1 we are going to start very soon. On week 3 course we are going to study about work, power and energy. Also we are going to cover conservation of energy and momentum. First, let's get into what we have learned before in the week 2 session. In the last session we have covered motion, frame of reference, motion with constant acceleration, inertia, Newton's law of motion, force, types of forces, momentum, and torque. These are the table of contents of today. It contains basics of work, power, and energy, work energy theorem, power, conservation of mechanical energy, principle of conservation of momentum. The learning objectives of the week 3 course would be as following. We are going to understand what is work, effect of direction of force on calculation of work, types of mechanical energy, conservation of mechanical energy, and conservation of momentum. So let's begin with work, power, and energy. What is energy? In very simple words, it could be explained as the capacity to do work is called energy. Since the energy is defined via work, thus its unit is same. It's joule and denoted by capital J. Let us try to understand energy using an example. A standing man is less energetic as compared to a running man. As you can see in the pictorial representation that when a man is standing, he looks very less energetic as compared to a running man. Also to mention here, standing is also a verb, running is also a work. Both standing and running is work. So the energy has been utilized in both the ways. While standing, a man utilizes energy, and while running, man utilizes energy. But when we have to say who is more energetic, then surely a running man would be more energetic than a standing man. Energy of an object is in motion is given as Ke is equals to half mv square, where Ke is kinetic energy. And let's get to know what is m and v. M is the mass of the body. In our case, the mass of the person. In this case, the mass of the person who is standing. In this case, mass of the person who is running. Similarly, v is velocity of the person. Like in this case, velocity of a person with which he is running. So m is mass of body and v is velocity of body. So kinetic energy can be represented as Ke is equals to half mv square. Further, Ke, that is kinetic energy of a system of objects, is the sum of kinetic energy of its constituents. Suppose there are multiple objects in a system. Thus, the total kinetic energy of the system would be is equals to summation of half mv square, where I is the number of objects in the system. Now, let us get to know what is kinetic energy in a straight line motion. Kinetic energy represents the energy possessed by an object due to its motion. So, if an object is in motion, it would definitely have some kinetic energy. The variation in kinetic energy is directly proportional to the speed. So, as we have already known in the previous slide that kinetic energy is equals to half mv square. So, this means that kinetic energy is directly related to the mass of the body and speed of the body. So does this statement denotes that kinetic energy is directly proportional to the change in speed. Let us assume two objects, object A and object B. Suppose an object A is coming downwards towards the earth. So it would be a free falling object coming from the sky. The force acting on object A would be equals to gravitational force of earth. Similarly, object B is thrown upwards. Since the object B is moving towards the sky due to the force exerted by a person, thus two forces would be acting on object B. The first force would be the upward force by which object B is thrown. The second force would be the gravitational force of the earth. Both the forces, the upward force by which the object is thrown in the sky and the gravitational force that has been acted by the earth, would be in opposite direction. This system of two objects shows us that when object A was falling, then also kinetic energy was there in object, and when object B was going towards the sky, then also kinetic energy was there in the object B. So we can depict that kinetic energy, there is presence of kinetic energy in a straight line motion. This slide tells us the same thing. When a ball A falls towards the Earth's surface, the force of gravity will be in direction of its velocity. Hence, kinetic energy will increase. Let's see this in the figure again. When a ball A falls towards the Earth's surface, the force of gravity would be in the direction of velocity. As the ball is falling downwards, so the velocity would be acting in downward direction of A, and gravitational force would definitely act in the downward direction. So both velocity and gravitational force will be in same direction, thereby causing change in kinetic energy, and that change would cause an increase in kinetic energy. Similarly, when ball B is projected upwards, the gravitational force will oppose its velocity. Hence, the kinetic energy will decrease. Let's see this in figure. This is ball B, and when ball B is thrown upwards, then there will be an upward force acting on the ball, making it to move towards the sky, whereas the gravitational force will cause to pull the ball downwards. Therefore, both upward force and gravitational force would be in opposite direction. Also, since the ball is moving upwards, thus the direction of velocity would be upwards. Rather, we see that the direction of gravitational force is downwards. Therefore, both velocity and gravitational force will be in opposite direction, and this will cause kinetic energy to decrease. Now, let's study kinetic energy in a circular motion. That in an object, if the resultant force is acting perpendicular to its velocity, then the object's speed will not change. Thus, kinetic energy does not change. Let's try to understand this using the following table. Let the direction of resultant force be tangential to its velocity. Then the kinetic energy would change. The second case would be when the direction of resultant force is perpendicular to its velocity. Then kinetic energy will not change. Let's try to understand this using an example. Suppose an object is attached to a string and rotated at a high speed. An object, this ball, is attached with a string and it is rotated at a high speed. Then the tension and the velocity of the object are always perpendicular. Since the object is moving in the rotational motion or circular motion, thereby this string would act as the radius of the circle, and the object velocity would always be tangential to the circle. Thereby, this is the direction of the velocity of the ball, and this is the radius of the circular motion in which ball is traveling. Therefore, the tension does no work done in circular motion. Thus, as seen in picture, that this tension will cause zero work done on the ball, since this string tension and direction of velocity is tangential to each other. Thereby, work done is zero in circular motion. Next, we are going to study its derivation. From definition of kinetic energy, we can make out that kinetic energy is equals to half mv square, where kinetic energy with change of time can be written as dk by dt is equals to d by dt of half mv square. We are keeping time as an aspect to this equation. Thereby, Ke is written as dk by dt. That is kinetic energy with respect to time. Similarly, on the right hand side, with respect to time, the change in kinetic energy would be d by dt of half mv square, where k is kinetic energy, m is mass of body, and v is velocity of body. Thereby, reshuffling it, we are getting m dv by dt into v. Here, this has been done to write off, this has been done to get force here as an important factor of kinetic energy. Like we always know that force is equals to mass into acceleration. We can see mass here, mass of the body, and we already know acceleration denoted by a can be written as dv by dt. Since the force is tangential, thus it can be written as ft, and this complete thing can be grouped together to write ft, where ft is m dv by dt. ft is equals to m dv by dt, and v comes as it was here, thus it is here. So kinetic energy can be written as ftv, where ft is the resultant tangential force. How it is calculated? The resultant tangential force is calculated as mass of the body into change of velocity per unit time, that is acceleration. Further, dk by dt can be written as ft into dr by dt. Here in this equation we have elaborated the v. V is velocity of the body, that can be written as dr by dt, where r is the distance traveled, and we already know that velocity is equals to distance traveled per unit time. Thus we have managed to elaborate v and have written this equation as dk by dt is equals to ft into dr by dt. Cancelling out time from this equation, we get that dk is equals to ft into dr. dk represents the work done, ft is resultant tangential force, dr is the distance covered by the object. Thus, dk is equals to ft into dr. One thing to be noted here is when the angle between the resulting force and the velocity is phi, then the resultant force becomes ft is equals to f cos phi. Let me explain that. When the resultant force and velocity makes an angle phi, then the resultant force becomes ft is equals to f cos phi. We have already studied that when the resultant force makes an angle 90 degree with the velocity, that is when the resultant force is perpendicular to the velocity, then the ft becomes f cos 90, which is equals to 0, since cos 90 is equals to 0. Thus, resultant tangential force would be 0. Now, in the next slide, we are going to study about the types of work done that we usually see. That is, when would be the work done would be positive, when would be the case where the work done would be 0, and when would be the case where the work done will be negative. This we are going to study in this slide. So, let there be 3 conditions for this. Let's get into the condition 1. Here, let's suppose the angle made by the force acting and the velocity is phi. Then we can see that if the angle is less than 90 degree, then the work done would be greater than 0. That is, the work done would be positive. Let's try to figure out that why the work done would be positive. As we already know that work done is ft cos phi, as we have studied earlier. Therefore, value of cos phi would be positive whenever the angle phi is less than 90 degree. we already know that cos 90 is 0. Thus, when value of phi is less than 90, then cos phi is always positive. Therefore, work done would be always positive. Coming to the condition 2, here we see that the force and the velocity both are acting perpendicular to each other. Therefore, the angle phi made between them is of 90 degree. As we have studied earlier, that work done is equals to Ft cos phi. And moreover, we already know from basic mathematics and trigonometry that cos phi, when phi is equals to 90 degree, is equals to 0. Thus, when the tangential force is multiplied by 0, it would give the result as 0, and thus the work done in this condition would always be 0. Coming to condition 3. Here, in this case, the angle phi made between the force and the velocity is greater than 90 degree. Thus, when, as we already know, that work done is Ft cos phi, and since the angle made between the force and velocity is greater than 90 degree, so from basic trigonometry, we get to know that when the value of cos 90 is 0 and when the value of phi is greater than 90, then cos phi is negative. Therefore, when negative value is multiplied by Ft, that is tangential force, then the net work done would be negative. Let me reiterate this complete situation. In condition 1, when angle phi was less than 90 degree, the work done would be positive. In condition 2, when angle phi was equals to 90 degree, the work done would be 0. In condition 3, when angle phi is greater than 90 degree, then work done would be negative. Now let's get to know what is work energy theorem. Work energy theorem. Let dk is equals to Ft into dr, and this dk is equals to Ft into dr can be also written as k2 minus k1 is equals to Ft into dr. How this came from? Let us refer to the previous slides. Here in the last equation, we have seen that dk is equals to Ft into dr, where dk represents the work done. Ft is the tangential force acting on the body and dr is the distance traveled by the body. Thus, coming back to our slides, we see that we can write dk as k2 minus k1. That is difference in kinetic energy. K2 minus K1. K2 be the final kinetic energy, K1 be the initial kinetic energy. Then K2 minus K1 is equals to Ft into dr. Hence, the resultant force does work on an object that is equal to its kinetic energy change. This line depicts the same. The change in kinetic energy directly be equal to resultant force of the work. Let F1, F2, F3 and there be n number of forces acting on the object. All forces are separated to each other, and when the object is subjected to these n number of forces, then the work done by the resultant force on the object is work done is equals to F1 plus F2 plus F3 plus dash 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 up to the Fn into dr, where Fn is the force exerted on the object by the nth term. The unit of work is Newton meter or joule, where joule can be represented by the capital J. Next, we are going to study how can work be calculated. For understanding that how work can be calculated, we have to refer this figure. Here, a mass of block is attached with the spring, and there are three cases of the spring. In case 1, the spring is at its natural length. In case 2, the spring is compressed by an amount x. And in case 3, the spring is elongated by an amount x. The same things are mentioned here. A spring can be positioned in three different ways. the spring in its natural length, that is case 1, the spring when it is compressed by an amount x, and the case 3, spring elongated by an amount x, that is our case 3. So we would be calculating the net work done by the spring on the system. Let us assume that the initial state of the spring is natural and the final state of the spring is compressed. And if x1 is the position of the initial state of the spring and x2 be the state of final stage of the spring, thus in this case when the spring was at natural state in its initial state, then x1 would be 0, and when the spring is at final state and it is compressed, then x2 will be minus of x. Therefore work done by the spring would be minus of 1 by 2 kx square. Coming to the next condition, let us assume that the initial state of the spring is natural, that is case 1. Then the final state of the spring is elongated, case 3. Then the distance traveled by the spring would be x. The distance traveled would be x. Therefore x1 would be is equals to 0, x2 is equals to x. Thereby work done would be half kx square. In another case, we can see that if the initial state of the spring is elongated, case 3, and the final state of the spring is natural, case 1, therefore the position of the spring at initial and final stage would be x1 would be is equals to x initially and x2 would be is equals to 0 finally. Therefore the net work done would be is equals to half kx square. In the similar manner, if the initial state of the spring is compressed and if the final state of the spring is natural, that is we are talking about the initial state compressed, that is case 2, and the final state, that is case 1, natural length of spring. There we can see that at initial position of the object would be minus x and final stage would be 0. Then the net work done on the object would be half kx square. Coming to last two conditions, let the initial state of the spring be elongated, case 3, and let the final state of the spring be compressed, case 2. Thereby we would see that the initial point, the position of x1 would be x, the position of x2 would be minus x at final stage. Thus the net work would be done is equals to 0. The last condition states that when the initial state of the spring be compressed and the final state of the spring be elongated, that is we are talking about case 2 and case 3 again, where case 2 is our initial state of spring and case 3 is our final state of spring. Thereby the values of x1 would be minus x and the value of x2 would be plus x. Thereby the net work done by the spring would be 0. If we try to make this table more easy to understand, then we can see that the net work done at the final state of the spring minus the work done at the initial state of the spring. Here the work done at the final state would be minus half kx square minus 0. Therefore net work done is minus half kx square, where k is spring constant, x is the distance covered by the spring. Here on this note, we are going to close our session 1. Thank you.